Our next speaker is Dr. Shiji Lin. She's a postdoc from the Hong Kong University of Science and Technology. Her interest is focused on interfacial fluid mechanics. Right away, she will introduce the big world in the small droplet. The floor is yours.
Hi everyone, I'm Shiji Lin. My topic today is unveiling the dynamics of drop impact-induced interfacial phenomenon, insights and applications. My presentation consists of the following 5 parts. Let me start from the background. Drop impact is a common phenomenon that occurs in nature and our daily life. The most popular phenomenon is the rain droplet impacts on the lotus leaves. We can see from this video, after impact, the rain droplet can rebound or breaks up into thousands of satellite droplets. Drop impact has a lot of applications, including the agriculture and inkjet printing. Recently, a lot of new technologies have been developed based on drop impact, such as mass transport, energy generator, and heat transfer. Drop impact is determined by liquid property and surface properties. According to different impact conditions, different phenomena may occur, such as the deposition, partial rebound, complete rebound, and splash. In general, we use 2 non-dimensional parameters to characterize the impact conditions, the Weibull number and the Rayleigh number. The Weibull number is the ratio of inertial force to the surface tension force, and the Rayleigh number is the ratio of inertial force to the viscous force. This figure shows the experimental setup that includes the high-speed camera and a lifting table and etc. By adjusting the lifting table, we can control the impact conditions. Drop impact process can be divided into spreading and retraction processes. In the spreading process, before impact, the droplet is spherical. After touching the solid surface, the droplet will be deformed into a pyramidal shape. Then the droplet radius is also increasing. Until reaching a maximum value, it will recede. One key parameter to characterize the impact outcome is the maximum radius, or its non-dimensional value, the maximum spreading factor, that is beta max. Why beta max is important? Because in practical applications, beta max can affect the surface coverage, heat transfer, energy conversion, and etc. We combined the experiments and simulations to understand how beta max is influenced by impact conditions and how it varies. What are the dominant parameters to affect the beta max? With this knowledge, we can control or optimize the impact outcome and according to our requirements. Except the spreading and retraction, liquid instability can also be triggered by drop impact. As shown in this first video, after impact, a lot of small droplets are ejected in the radial direction. We call it splash. It is interesting to find that surface temperature can affect splash occurrence. By increasing the surface temperature, splash can be suppressed. However, by further increasing the surface temperature, splash occurs again. The dependence of splash occurrence on surface temperature varies with surface roughness. On rough surfaces, the splash occurrence is less dependent on surface temperature. We summarize the critical occurrence of splash on surface temperature and on surface roughness. We developed a theoretical model to understand the relationship between these parameters. And with this knowledge, we can understand. And the theoretical model provides agreement with experimental results. The liquid instability not only occurs in the radial direction, but also in the vertical direction. As shown in this video, after impact, a bubble is entrapped in this droplet and a singular jet is shot out. Let's look at the evaluation of the sanguine jet in a higher resolution. We can see that in the rising process, it is not stable. The neck of this sanguine jet gets thinner and thinner until a critical point is reached. Afterwards, a secondary droplet is shot out. By analyzing the fluid flow during the printing process, we can understand the relationship between the sanguine jet and the secondary droplet size. Furthermore, we find a power law relationship between the secondary droplet size and the initial impact conditions with a number. By simple scaling analysis, this power law relationship can be explained. Let me introduce the impact of compound droplet. Compound droplet consists of multiple phases. To compare, I repeated the impact of monophase droplet. As shown in this figure, we can see a bubble is entrapped after impact. However, for compound droplet with a small oil core, we can see the bubble entrapment is suppressed. By further increasing the oil core inside the compound droplet, a new phenomenon, that is, a water is entrapped inside the oil core. In total, we observed 6 different phenomena for compound droplet and summarized this phenomenon in this figure. With understanding of the conditions for each impact phenomenon, we can understand and control the impact outcome and take advantage of each phenomenon. For example, based on the water entrapment of the inside the oil core, we proposed a new method to produce the micro-sized compound droplet, as shown in this figure. Before impact, the compound droplet is double layered, but after impact, it is 3 layered. And when the water shell dissolved, we obtained a micro-sized compound droplet. In the past, compound droplet can only be formulated in microfluidics, but it is complicated. However, the drop impact method can provide an easy method to produce compound droplet, micro-sized compound droplet. And this method can also adjust the resultant compound droplet. With the understanding of drop impact, we are wondering whether we can go further for the application of the drop impact. The answer is yes, if we think more. And thus, we proposed a new design for the impact system, as shown in this figure, and to collect the secondary droplet based on the sanguine jetting. This idea is approved by this video. We can see that the micro droplet is generated here, and it can be collected here. Based on this, we proposed a new device that is to dispense liquids, and we compared our liquid dispenser with existing ones. Each technology has its own advantages, including the pipette or inkjet printer, etc. But these technologies have a similar limitations, that is, it is hard for them to dispense liquids with controllable volume. Fortunately, the drop impact-based liquid dispenser can adjust the liquid volume from hundreds of picoliters to hundreds of nanoliters. With the capability to dispense liquids, we can achieve the controlled microchemical reaction. And because this method is non-contact, so we can achieve multiple chemical reactions in a single procedure without contaminations. Furthermore, this device can be used in microfabrications. To conclude, we investigated the impact of monophase droplet and compound droplet. With this knowledge, we explored its potential applications. Finally, I would like to give acknowledgement to my supervisors, collaborators, source funding providers, and as well as URSS, which give us the opportunity to learn from each other and make new friends. Thank you.